Hi everyone, welcome to lecture number 8. This is another joint lecture between the Calc and non-Calc students. This lecture doesn't have any calculus and it doesn't require any calculus. Okay, up to this point in the course, we've been studying kinematics, and kinematics is just one part of what's called classical mechanics. It emphasizes questions of the mathematical description of motion. Okay, so we did things like looked at motion in 1D, whether it was just like moving, accelerating in 1D, or oscillating back and forth in 1D. And we looked at motion in 2D, was like projectile motion or uniform circular motion. And we asked questions like where is this object at a given time, how fast is it going at a given time, and what's its acceleration at a given time. And there were formulas to do that, and this all goes under the heading of kinematics. Okay, but this is incomplete because you might want to ask the question, well, what causes that motion? So when you throw something up into the air, it forms a parabolic path, as you saw a few lectures ago, and that parabolic path is because there's constant acceleration downwards. And you can say, well, why is that? Why is it constant acceleration downwards? And why does that lead to the parabola and so on? So as soon as you ask the question, what causes the motion, then you're moved into a new area of classical mechanics, which is known as dynamics. So dynamics is basically what causes the motion, not just a mathematical description of it. You need the mathematical description first before you can start asking what causes this motion. But once you have a handle on the formulas that describe the motion mathematically, you would naturally ask, well, why does it do this and not something else? Like, there are like these medieval documents that show how a cannonball goes, and they would show it. They would actually draw it like it moves up and along a line, runs out of this thing they called impetus, and then it just drops straight down. So for them, projectile motion was like up and then straight down. We know that's not true. Okay, it's a parabolic curve like that. Okay, and you say, well, why is it that and not the other one? So out of all the possible motions, why do we get this particular motion? And this is known as dynamics. It's actually even easier than just asking what causes this motion. It's really comes down to what causes the acceleration, okay, which you'll see when I give you Newton's laws in a minute. All right, so this is what we're going to be studying next, and the rules that govern this, the laws that govern this, are known as Newton's laws. Okay, and there are 3 of them. They're not that mathematical; they're much more conceptual. And so this particular lecture is going to concentrate on the conceptual elements of Newton's laws, and with a few examples in there, but they're really simple examples compared to what we're going to do next. Okay, before I give you Newton's laws, I got to introduce some new concepts, some new physical concepts. Okay. So the first physical concept that I need to give you is the concept of a force. All right. And what is a force? Well, it's just very trivially defined as any push or pull. Okay, it's almost too trivial. And a lot of definitions in physics are like that. You say, well, but you want to be precise. I know. The way to become precise in physics when you have a physical concept is to describe what experiment gives you that physical quantity. Okay, and so just intuitively you could say, yeah, a force is any kind of a push or pull. I have some object and I push on it, I'm exerting a force on it. Or I have a rope and I'm pulling on it, that I'm exerting a force. Okay, so anything that's a push or a pull is a force. But to make this precise, how do we measure a force? Okay, and to measure something, of course, you need an instrument to measure it, and the answer is to what instrument is used to measure a force is a spring. Okay, so what I have here, these simple diagrams, is I have a spring, and this diagram right at the top here, the line with the hashes, this is like a ceiling or some fixed bar or something that I can attach a spring to. Okay, so I've got this like bar here, and I'm just going to attach a spring to it, and you can see here's my spring. Okay, and I haven't put anything on the spring, so the spring is just sitting there. And it might be bobbing a little bit, but we'll wait till it stops bobbing and stops moving. And there's the spring sitting, and we'll call that x equals 0. This is the equilibrium position of the spring. Okay, and the next thing is that I catch a fish, and I say, well, how much this fish weigh? Okay, what's the force of gravity on this fish? And I'll put the fish on the spring, and you know what will happen. The spring will extend. Again, it might bob up and down because there's oscillation, but we'll wait till that settles down, and then we can look at how much the spring stretched. okay? And the degree to which the spring is stretched is how much pull gravity has on that fish, okay? And then I might catch a bigger fish and I put it on my same scale and it might stretch it some more, okay? And so you go, oh, this is, this is interesting. The more force there is on the spring, the more it stretches the spring. And so I can equate or I can at least make a proportionality between how much the spring stretches and how much force there is on the spring. Now I did it here to weigh, to find the weight of a fish, but you can imagine you just hold on to this spring and, here's the spring and you go, okay. And then you say, I'm going to exert a little bit of force. Then it stretches a little bit. I'm going to exert more force. It stretches more. I'm going to exert more force and it stretches more. The more force you exert, the more it stretches. Okay. Now all springs will eventually break and so on. So this is within some, what's usually called the elastic limit. Okay. And so you can use a spring to measure how much of a push or a pull there is. That's more or less pulling. What I'm showing here is pulling, but some springs, they compress. And so you can imagine a spring which is this long and you say, well, I'm going to push it. I'm going to push on the spring. I push a little bit. I push more, and so on. Later, we'll actually give you the formula for this. It's known as Hooke's law. But for now, this is good enough. Just recognizing that I can measure this push or pull by using a spring. And how much the spring stretches or compresses is proportional to how much force is being exerted. Okay, so that's concept number one. We need that concept before I actually give you Newton's laws. Okay, here's concept number two. It's mass. All right. And again, the definition I have here, it's pretty vague. It's just the amount of substance present. And you go, geez, that's so vague. How do I work with that? How do I even think about that in when I go to solve problems? Well, right now, just stick conceptually, and the answer to what is mass, the definition of what is mass, is the procedure and the instrument by which you measure that. And mass is measured with a balance. Okay, a balance. All right, not a spring. Okay, so and we'll get to the difference between weight and mass in a minute. So let's just stick to this mass. So what I need, of course, whenever you're doing this is some kind of a standard. And so I'm going to get a standard, and the standard that we're actually, the MKS standard is 1 kilogram. But right here I have like 1 gram, okay? And a gram is actually defined as the mass of 1 cubic centimeter of water. Actually, 1 cubic centimeter of water at 4 degrees Celsius. Next semester, I'll tell you why 4 degrees Celsius, okay? So, a centimeter is about this big. If you make a cubic centimeter of water, the mass that's in that cubic centimeter of water, that is 1 gram, okay? So great, we have the standard, and once you have the standard for a mass, you can put it in a balance in one of the pans, okay? Well, actually, first you gotta calibrate the balance, which means imagine that you've got 2 pans here like this, all right? So there are the 2 pans. Imagine there's nothing in them, all right? And then there's a beam across the top, and then there's this thing called a fulcrum here, okay? And what you do is you move the fulcrum back and forth until the pan balances. Okay, so they're balanced like that. The 2 pans don't have to be the same size, because as soon as you've got the fulcrum in the right place, they'll balance. And then you put a 1 gram mass in one of them, and of course that side's going to go down. And now you want to weigh out, find the mass of some unknown substance. Say you want 1 gram of that unknown substance, you keep sprinkling that unknown substance into the other pan until it balances out again, and then you can say that that 1 gram there is equal to the 1 gram of the substance that you wanted to weigh out. Okay, so this is known as a balance. Okay, now the reason we really need to distinguish between weight and mass, and I'll give you a little bit more on this later, is because mass, the amount of substance present, doesn't depend on the force of gravity. Okay, so if we go back to my fish example here, see, we live on the Earth, and so because we live in only one particular strength of gravitational field, G is equal to 9.8 meters per second squared down, we tend to confuse mass and weight, okay? So if I have my fish, okay, this fish right here, and I weigh it on Earth, I just get the force of gravity on Earth, it'll stretch my spring a certain amount. But if I take the same apparatus and I take it to the moon, the moon's gravitational field is about 1/6 that of Earth. Well, guess what? The same fish will stretch the spring only 1/6. Okay, so if on Earth it stretches at 6 centimeters, on the moon it'll only stretch at 1 centimeter. Why? Because the weight of the fish on the moon is less. Okay, and then I can go into deep space where there's no gravitational field, and in deep space the fish has no weight and it wouldn't even stretch the spring at all. Okay, so you could see that this fish, which is the same in all of my scenarios, on Earth, on the moon, and in deep space, the fish, which is the same, has a different amount of force of gravity on it, or weight, and therefore stretches the spring a different amount. But so the weight of the fish changes depending whether you're on Earth, the moon, or in deep space. But what about the mass? So what was the definition of the mass? The definition of the mass was the amount of substance present. Well, it's not like the fish got smaller or bigger. Like, it's not like the fish gained atoms and molecules when you on Earth compared to the moon. Okay, there's the same amount of atoms and molecules on Earth as there are on the moon, the same amount of substance. So the mass doesn't change if you're on Earth or on the moon or in deep space, even though the weight changes. What what doesn't change, the amount of substance, can only be measured with a balance. So if you're here on Earth and you've got this 1 gram mass here, and you put the fish like some 1 gram of substance there, it'll balance out. If you take that same apparatus to the moon, even though the gravitational field on the moon is less, it'll still balance even on the moon. Okay? And in deep space, there's no gravity. Balances need a little bit of gravity. Doesn't matter how much gravity you have, you need a little bit of gravity. But even in deep space, you could do this, because you can spin it in some kind of, you can create a container which spins, and because there's a centripetal acceleration, the balance will work the same even in deep space in that accelerated frame of reference. Okay, and so yeah, the fish, the weight of the fish, that is the force of gravity in the fish, is different on Earth, the moon, or in deep space, but the amount of substance present is the same on the Earth, on the moon, or in deep space. And that's the biggest difference between mass and the force of gravity. Okay, and so yeah, you need a balance to measure mass. Okay, so we've got the concept of force, we've got the concept of mass, and the third concept is not really a new concept, but because I'm introducing dynamics from scratch, the third concept that you need to understand Newton's laws is acceleration. But you already know what acceleration is. Acceleration is speeding up or slowing down. Okay, it's the rate at which the velocity changes. All right. Okay, great. Now we can jump into Newton's 3 laws. All right. And Newton's 3 laws, he stated them in a book he called the Principia Mathematica, and written in the late 1600s. And fairly long book, very ambitious. But out of it, 3 laws are distilled, and this is not exactly the way he stated them. I've distilled down the language, in a way that's most appropriate for a freshman physics course. Okay, the first law is actually a special case of the second law. Okay, so you could even say there's only 2 laws, but no one ever does that. Everyone says there are 3 laws. But the first law is really a special case of the second law, and I'll show you that in a minute. So what does the first law say? The first law says that in the absence of any net force, and you know what a force is, but I got to explain this word net. Okay, so in the absence of any net force, an object at rest stays at rest, or an object that's moving keeps moving at a constant speed in a straight line. Okay, and let's think about this carefully. All right, so you have an object. The net force on that object is 0. That doesn't mean that there are no forces on it. It just means that the forces will all add up to 0. And I'll still have to explain net more carefully, because forces turn out to be vectors. Okay, so there might be a bunch of forces acting on it, or maybe no forces acting on this object. But whether you have no force or a bunch of forces, adding up all the forces adds up to 0. So there's no net force on the object. Well, then there's only 2 possibilities. Either that object is just not going to move, it just sits there. Okay, or the other possibility is, if it's moving, it's just going to keep moving at a constant velocity. That is the same speed, doesn't speed up, doesn't slow down, in a straight line, doesn't turn. Okay, doesn't speed up, doesn't slow down, and doesn't turn. Just keeps moving in a straight line like that. Okay, the law works both ways, in the sense that if you know the net force is 0, then you can conclude that it's either going to be at rest or it's going to move at a constant speed in a straight line. Conversely, if you see an object that's moving at constant speed in a straight line, you can go backwards and say, oh, the net force must be 0. So the logical implication is both ways. All right, it has to be, actually, for physical reasons, but I just thought I'd make that explicit. So if in a problem I tell you it's not speeding up or slowing down and it's moving in a straight line, your brain should immediately go, oh, the net force is 0. Or if in a problem I say to you the net force is 0, your brain should go, oh, it's either not moving or it's moving at constant speed in a straight line. Okay, so there's the first law. All right. Now, as I said, the first law is a special example of the second law. So what I'm going to do is I'm actually going to introduce the second law and illustrate both of them together. Okay, so here's Newton's second law. The first law says, well, there's constant velocity, and constant velocity in a straight line. Um, if you say that, then you're saying that the object doesn't accelerate, okay? Or if the object's not moving, then obviously the object is not accelerating. So Newton's first law really covers the situation where the object is not accelerating. This begs the question, will it accelerate, or under what conditions will it accelerate? And here's the answer. Newton's second law states that if there is a net force on an object, then the object accelerates in the direction of the net force according to the formula A is equal to F net divided by M. Okay? And just to describe the symbols, F net, this is the net force. Again, I got to unpack that a bit for you. M is the mass, which we just discussed, and A is the acceleration. All right. Let me read it again because this is by far the most important of the three laws. Okay, and we're actually going to use this to solve problems. So it's well worth understanding it at this point. If there is a net force, okay, then what's going to happen? The object is going to accelerate in the direction of the net force, according to the formula A is equal to F net over M. Okay. Now, this is one way that the formula is written. Sometimes you'll see it written as F is equal to MA. First, I don't like saying F is equal to MA because F, it's really F net, okay? Although, you'll see that in a lot of textbooks and so on, it'll just say F is equal to MA. All right, but the problem with saying F is equal to MA is that it doesn't emphasize in your mind that there might be many forces acting on an object. In fact, almost all of our problems will have multiple forces acting on an object. And you say, well, which one of those F's is the one that in F equals MA? It's all of them. You have to add them up. Okay, so F net equals MA. That's okay to say F net equals MA. But I just rearranged it to A is equal to F net divided by M because normally the way our problems go is we'll calculate F net by adding up all the forces as vectors. We'll divide by the mass, and poof, out comes the acceleration. Okay, and all right. So there's the second law. Let's illustrate both of these laws. Okay, so first, a little less than an example here, just kind of a quick illustration here. What do we mean by this net force? Okay, it has to be calculated as a vector. So force is a push or a pull, but you're pushing or pulling in some particular direction. Okay, and so you could push in the positive x direction, you can push in the negative x direction. In 2D, it could be in positive y or negative y, or at any angle in between. Okay, and so that's important. So I tried to illustrate this to give you some intuition into what's going on by asking you to consider an ice rink. So we're looking down on this ice rink here. Okay, and we have this box on an ice rink, and the reason it's on an ice rink is so that there's no friction. All right, and someone is going to, maybe you attach some ropes to this box here, and someone's going to pull it this way with a force F1, and someone's going to pull it this way, up like that, F2. Now, we're looking down on the ice rink, okay? So this is not up, okay? This is like, I don't know, in the north direction, and this could be like in the east direction or something like that. And you might ask yourself, well, which way is this object going to accelerate? And it's going to accelerate because there's a net force on it, and Newton's second law says if there's a net force, there's going to be an acceleration. And so we have F1 here and F2 here. We have to do a vector sum between F1 and F2. So remember I showed you how to do vector sums. You basically graphically you put the tail to the head of the second vector and so on. And so F net is going to equal F1 plus F2. You can think about it graphically that way, but we also have an algebraic way of adding them. The net force is going to be on some angle here like that, okay? And so here I've just got F net drawn out. There's F net, which is the sum of F1 plus F2. And I didn't give you any numbers here, but if you had the mass, you divide F net divided by the mass, that would give you the acceleration. So you would have a number for F net, you have a number for the acceleration. You go, well, what direction is the acceleration in? The acceleration is in the direction of F net. So if F net is on this angle here like that, that's the direction in which it would accelerate. It wouldn't accelerate along F1. It wouldn't accelerate along F2. It's going to accelerate along an angle between the two, which is the angle at which F net is pulling. Okay, and so there you go. There's a brief introduction into Newton's second law. Okay, how is Newton's second law a special case of, or Newton's first law a special case of Newton's second law? Well, let's take a look here. Let's go back to the formula, and here we have F net divided by m is equal to a. Well, suppose F net is 0, because Newton's first law says in the absence of any net force. In other words, if F net is equal to 0. Well, if F net is equal to 0, okay, it doesn't matter what the mass is. If 0 divided by any number is 0. So if F net is 0, then A must be 0. Conversely, if A is 0, then F net must be 0. If A is 0, what does that say? Well, it says that there's no acceleration. So if it's moving, it has to move at constant velocity, straight line. Okay. Remember, if you're turning, remember uniform circular motion. If you're turning, even if you're moving at the same speed, but you're turning, there's an acceleration. So as long as you're moving at the same speed in a straight line, you're not accelerating. So if F net is 0, the acceleration is 0. You move at the constant velocity in a straight line. Or if you're not moving at all, your velocity is 0, then you stay at 0 velocity. Okay. So Newton's second law is really the only thing you need, because the first law is just the second law with F net equal to 0 in it. Okay, so the two laws are totally consistent with one another. The reason the first law was important was because there was this kind of a vague idea that people had in their mind that if you don't push on something, then it'll slow down. Okay, that's true, but that's not the full story, because people didn't realize this didn't know about friction. Okay, but I'll illustrate that in a second. Okay, so there you go. Before I jump into some really simple problems here, let's look at the units so that we understand what the units are of acceleration, mass, and force. Okay, so those are the three dynamical quantities. Okay, acceleration, mass, and force. Okay, so acceleration, we already saw the units of acceleration, meters per second squared. Okay, the units of mass are kilograms. Okay, so that's what we chose for MKS. It might seem strange. You might say, why isn't it the gram? I'm not really sure about the history of why MKS chose the kilogram, but it is the kilogram. That is the fundamental unit of mass. Okay, in the standard system, a kilogram is about 2.2 pounds, just to give you an idea of how much a kilogram is. But if you go to the store and you buy like a bag of sugar, most of those bags of sugar are about 2 pounds or 1 kilogram bags. So that gives you an idea of how much 1 kilogram is. Okay, and finally, what's the unit of force? Well, if you start from the formula A is equal to F net divided by M, and you rearrange it into perhaps a more familiar form, but less useful for us. Okay, F net equals MA. Well, the units of M, they're kilograms, and the units of A, they're meters per second squared. So the units of force are going to be kilogram meters per second squared. Okay, that is correct, but whenever we start to get units which are longer and longer and longer, remember there are only three fundamental measurements. Okay, length, time, and mass. Okay, well, there's information, but we don't use it in this course. So length, time, and mass. You see them here. There's the mass. There's the mass, kilograms. There's the length, meter, and there's the time, seconds. Okay, but as our units get more and more complicated, sometimes it's useful to just like abbreviate them and give them a new name, and that's what we do with a kilogram meter per second squared. We could continue through the whole course, and every time you have force, you just write down kilogram meter per second squared, and you'd be fine. Okay, doing that, but that unit is often called a Newton, and you'll see me using a Newton. Okay, so whenever you see Newton in a formula, it's totally equivalent to kilogram meter per second squared, and vice versa. Okay, and sometimes we'll have to replace newtons with kilogram meters per second squared to see how the units work out. All right, and well, there you go. Okay, and so if you're a famous physicist like Newton was, I think Newton did this work in 1686. Okay, so years later, people realized that this what Newton had done in the Principia Mathematica was a very brilliant thing, and so now in honor of Newton, we call this a Newton, capital N, like that. Okay. All right, so now let me do some more problems. These are really simple problems. They're not at all indicative of the kinds of problems that we're going to do in the next lecture. But these are more problems to try to illustrate these laws, because they're purely conceptual at this point. There's very little in terms of mathematics. Well, maybe the vector is a little bit difficult, but other than that, it's pretty straightforward. Okay, so I have an example here, and I didn't even write the full English for it. It's just a simple example. We have a road and we have a car which is driving down the road, and the car is moving at a constant speed of 50 kilometers per hour, okay, which is the usual speed you have in a city. So 50 kilometers per hour and along a straight line. Okay, so as soon as you hear that, you should say, aha, no acceleration. constant speed, straight line, no acceleration. And which law applies to that? The first law. Okay, so I go on, and then question number 8, I say, suppose the car has a weight of 10,000 newtons. What force does the ground exert upwards? Okay, now let's be very careful. It's very difficult in English when you say, what's the mass of something. You could say what's the mass of something, but we like to say what weighs something. You weigh something. But when you weigh something, do you want its weight or do you want its mass? Because the two are different. So let's be very careful here. When I say the weight, I really mean the force of gravity on the car. Okay, and you could see that the weight is not in kilograms. The weight is in newtons. All right. So the weight of an object. I'll try to be very careful with the language, but it's hard because in colloquial English, we don't always we're not always very clear about the difference between mass and weight. Okay, so but I'm going to try to be very careful in the course. So when I say weight, I mean the force of gravity, and because force of gravity is a force, that's in newtons. So the car weighs 10,000 newtons. Okay, and I want to know what force does the ground exert up on the car. Okay, well, let's take a look at the forces on the car. Now, I didn't give you all information. There might be more forces, but you do know one thing. Since we're in the situation of Newton's first law, because there's no acceleration, constant velocity, straight line, all the forces have to add up to zero. They have to add up to zero. Now, which way does the force of gravity act? The force of gravity acts downwards. So you can see it here. I called it Fg. Fg is 10,000 newtons down. Okay, and I put a little dot in the middle of the car. Force of gravity acts everywhere in the car, but let's not worried about the spatial extent of the car. We'll actually worry about that later in the course. But right now, there's this overall force of gravity on the car, and it's downwards, obviously, because gravity pulls down. And Fg is going to be 10,000 newtons down. Okay. Well, never mind this Fn up here. If that's all there were, then the forces wouldn't balance out. Okay, so there has to be something that balances out the force, otherwise you'd have an acceleration. Otherwise the thing would be falling. Okay, and if you look here, I drew a force upwards and I called it Fn. And what is this force? Well, why doesn't the car fall? Why doesn't it go down? Well, because the road is pushing it up. So Fn is the effect of the road pushing up on the car. All right, and it has to also be 10,000 newtons. Why? Well, these are vectors, and if you have something which is pulling 10,000 newtons down, you have to counteract that to get a zero net force, 10,000 newtons up. Okay, so gravity pulls down with 10,000 newtons. The normal force pushes up with 10,000 newtons. So what is this thing called a normal force? Because I just introduced it, introduced that term, normal force. That's basically whenever two objects are touching, the force between them is known as a normal force. Okay, so if that's not totally clear right now, that's okay. It's going to become increasingly clear as we start to do problems. Okay, so the force of the ground pushing up, the ground is touching the car, pushing up on the car. That has to be 10,000 newtons. It has to exactly balance the 10,000 newtons down from gravity. Otherwise, if the gravitational force were bigger than that normal force, so there were no normal force, then it'd be unbalanced. And there would be a net force. And if there is a net force, what do? You get an acceleration in the direction of the net force. But there is no acceleration by, how the problem is set up. And therefore, it's impossible for there to be an unbalanced force. Okay, so the force of gravity here, 10,000 newtons, has to be balanced against the 10,000 newtons up. Okay, there you go. There's a very simple illustration of Newton's first law. Okay, so I now have part B here, and in part B, what I say, okay, is imagine that the engine is actually pushing forward with 3,000 newtons. Okay, so never mind this frictional force back here. We now have, I called it Fe for the force due to the engine. Okay, so the force due to the engine is 3,000 newtons and it's pushing forward. So now we have identified three forces. We have the force of gravity down, 10,000 newtons, being balanced again against the normal force, 10,000 newtons up. And we have 3,000 newtons forward because the car is being pushed forward by the engine. And I asked the question, what is the force of friction? Well, the force of friction has to be in the opposite direction to the direction that the engine is pushing, and it has to be the same magnitude. So it's 3,000 newtons in the opposite direction, and that's how I came up with this force of friction. Now, on Earth there's air, and when you're driving, the air causes air friction. And like every kid has put their hand out the window when you're driving, and so you can feel the air pushing back on your hand. Well, the air doesn't just push back on your hand when you're driving, it pushes back on the entire car. So if the car didn't have a forward force, it would eventually come to a halt. But if the car is pushing forward with 3,000 newtons and it's moving at this constant speed, then that 3,000 newtons has to be exactly balancing out whatever the drag is due to the force of friction of the air. And that's 3,000 newtons back. Okay, so that's how I reasoned this out. All right, so again, I just simply stated, look, the engine is pushing forward with 3,000 newtons force. What is the force of friction? And the answer would be the force of friction is 3,000 newtons in the opposite direction. Okay, take a look at this diagram very carefully, because now you're starting to see the vector nature of the force. The forces up and down have to cancel. Okay, forces up and down don't cancel against forces left and right. Forces up and down cancel against one another, and forces left and right cancel against one another. Okay, all right, it's not like that 10,000 newtons has to cancel against the 3,000. That makes no sense, because they're perpendicular to one another. Like one's along an x-axis, the other one's along a y-axis. And remember when we did Cartesian vectors, x components add to x components, independent of y components, which add to one another. Okay, and so the force up and the force down balance, and the force to the right and the force to the left balance independently of one another. Okay, now when we go to do problems, we're going to have vectors in all different directions. Okay, not too complicated, but they will be in many different directions. The trick in solving those problems is to actually resolve all the vectors, that is, break up all the vectors, so that you only have vectors going up and down, or vector components going up and down, and vector components left and right. In other words, we're going to take our vectors, convert them to Cartesian, and then, in Cartesian, adding vectors is very, very easy, because x components add to x components, and independently y components add to y components. Okay, so I'm getting a little bit ahead of the game, but this kind of cross pattern that you're seeing here is going to be very important. As soon as you get your forces in this kind of a form, where you have forces up and down and forces left and right, then you can go ahead and solve the problem very easily. Okay, all right, and I do want to say, before I go on to my next example, make more clear what I already alluded to above, and that is the difference between weight and mass. Okay, so if you have the mass of something, that's the amount of substance, you can actually calculate the weight from the amount of mass. And you say, well, how do you do that? So if you take a look here, I've got a simple picture of some, I don't know, a ball or some object here with a mass m. Okay, now this ball, if it's, you let go of it in space, it's going to fall. And when it falls, it's going to accelerate with an acceleration of 9.8 meters per second squared down. Or we approximate that in our problems to 10 meters per second squared. So we have a mass, we have an acceleration. And if you have a mass and acceleration, you can say, that sounds like Newton's second law. I have a mass, I have an acceleration. Shouldn't I be able to calculate the force that causes that acceleration? And the answer is yes. There's your Fg. So whether the object is falling or there are other forces, it doesn't really matter. But you've got this force Fg. You can now relate Fg, the force of gravity. So that subscript g there, that's not F times d. That little subscript g just means force due to gravity. You'll see me, when I write forces, I'll often write an F to mean the force, and then I'll put a little subscript to indicate what's causing that force, or what kind of force it is. Okay, so just very quickly, just go back here just to show you how the notation. Fn, the normal force. Fe, the force due to the engine. Ff, the force due to friction. Fg, the force due to gravity. Okay, so here we have Fg, and Fg is the force due to gravity. There's m, the mass, and g, and you go, how do they relate to one another? Well, F net equals ma, and so you could just say, using Newton's second law, that the weight of the object, that's Fg, is equal to mg, like that. Okay, so last thing before I do this very simple problem here, Fg, there's two ways to think about it. You could say it's the force due to gravity or the weight. The two words are totally synonymous with one another. Force due to gravity and the weight of the thing. Okay, don't confuse, those are synonymous. Don't confuse that with mass, which is the amount of substance present. Okay, very simple example. You go to the store and you buy that 1 kilogram bag of sugar. All right, if I asked you what is its weight, I'm asking what's the force of gravity on it. Its mass is 1 kilogram, but what's its weight? And the weight is F is given by Fg is equal to mg, like that. Mass 1 kilogram, g is 10 meters per second squared. Multiply the two together and you get 10 kilogram meters per second squared, or 10 newtons. Okay, and so you conclude that 1 kilogram weighs 10 newtons on Earth. Now, why did I say on Earth here? And the reason is that's g. G is 9.8, roughly 10 meters per second squared on Earth. Okay, if I wanted, if I wanted in the middle of a problem or in some problem, I could say to you, what's the weight of that 1 kilogram mass on the moon? Well, then I would have to give you G for the moon, and it wouldn't be 10. I think it's like 1.6 or something like that. Don't quote me on that, all right? But it's a smaller number, okay? And of course, you still have 1 kilogram because there's still the same amount of substance there, okay? It's not like it loses substance by going from the Earth to the moon. There's just as many molecules, atoms, and molecules in there. But the acceleration due to gravity is different on the moon than it is on Earth, and therefore its weight is different on the moon as it is on Earth. Okay, so we won't do a lot of problems on the moon, but I needed to bring that up here to emphasize that, yeah, there's another component to weight. It isn't just the mass, it's also the acceleration due to gravity. You could see that, before Newton, when people didn't distinguish in their mind the amount of substance and the weight, that, they didn't know about G. They just did not know about G at all. And so, yeah, at that point, there was no distinction between weight and mass. But now, with Newton's laws, we really need to make that distinction. Okay, so another problem, because the problem I did so far was really just illustrating the first law. Let's try to illustrate the second law. Okay, so the driver of the car in the previous example steps on the gas such that the engine pushes forward with 4,000 newtons. Okay, what is the net force? Let's assume that the friction stayed the same. Okay, and so we have the following free body diagram, as it's called. Okay, so what is a free body diagram? And that's basically just a diagram with all the forces attached to the object. Okay, and if there are two or more objects, and we'll have problems like that, then you just isolate one object at a time, and you say, what's the free body diagram for this object? What's the free body diagram for that object, and so on. Okay, well, we only have one object here of interest, and that's the car. So this is the free body diagram for the car. And when you do these problems, the first question you have to ask yourself is, what are all the forces acting on the car? So like in kinematics, remember, you drew the picture, and then you drew the rulers, the coordinate system on top of the picture, and then you identified the quantities. Roughly the same thing here. You draw the picture. Okay, so here's the car. You identify all the forces on the object. All right, so what are all the forces? Well, there's almost always gravity, because we tend to solve these problems on the surface of the Earth. So here's the force of gravity, which we know are 10,000 newtons. Okay, we know there has to be a normal force because the thing isn't accelerating up or down, and that normal force is 10,000 newtons. We know there's a force of friction of 3,000 newtons. That comes from the previous problem. Okay, I'm assuming that the force of friction didn't change just because you're accelerating, but this time the force that the engine pushes forward is 4,000 newtons. Okay, so this is the next step. So the first step is draw the picture. The next step is identify all the forces that are acting on the car. Okay, there are more steps before you do the next thing, which is add them all up. But right now, there's a coordinate system here, but it's pretty trivial in our case. Okay, so I'm going to say x is horizontal and y is vertical. And at this point, you could say, well, let's add up all the forces. Okay, so with all the forces, you could say, well, there's a normal force up and the gravitational force down. So look at the forces up and down, the y forces, and they cancel out. Okay, sometimes when forces cancel out in the free body diagram, you'll see these double hashes here. You can see how I added them to the lines. That just is these two forces cancel. It's just a graphical way of showing the reader that these two forces are canceling. Okay, the force forward, the engine force and the frictional force, they don't cancel, so you don't want to put any hashes on those to show that they cancel out. So it's 3,000 newtons back, 4,000 forward. Which one wins? Well, the engine forward wins, and by how much does it win? By 1,000 newtons. Okay, so the 10,000 up, 10,000 down, they cancel. The 3,000 back and the 4,000, they don't cancel, but there is a leftover force of 1,000 newtons forward. Okay, and so you could, if you need to, you can even redraw the diagram. There's the diagram redrawn with just the net force. All the other forces having been added up together, having been summed up, you get a net force forward of 1,000 newtons. Okay, so the net force is 1,000 newtons forward, okay? And it's important to keep the direction in mind, all right? I mean, we don't have to be super formal about it, but, you know, in the diagram, draw the direction, because remember, the acceleration is going to be in the direction of the net force, okay? And so there it is drawn there, and there it is in English, okay? Draw it forward and then just say forward like that. Or you could say in the positive x direction as well, okay? Now, for the acceleration, how do you calculate that? Because that's what I asked for. And the acceleration is a is equal to F net over m. Okay, and you go, well, I've got my F net, it's 1,000 newtons, but I don't have m. But you really do, okay, or indirectly, yeah, you do, okay. And the reason is the car has a weight of 10,000 newtons. So if it has a weight of 10,000 newtons, remember Fg is equal to mg. All right, so if Fg is 10,000 newtons and g is 10, 10,000 divided by 10 tells you that the mass has to be 1,000 kilograms. The relationship between weight and mass is very easy if you approximate g as 10, because the weight is always 10 times bigger than the mass. Okay, so the mass 1,000 kilograms, the weight 10,000 newtons. Okay, just multiply by 10, that's g, and you'll get the weight. All right, or here I went backwards. I know that the weight is 10,000 newtons, so the mass has to be 1,000. So indirectly, by my giving you the weight, I have told you what the mass is. All right, and so now we can go back to our formula. A is equal to F net divided by m. So that's 1,000 newtons, the net force, divided by 1,000 kilograms, and that gives us an answer of 1 meter per second squared. So the car would accelerate forward at 1 meter per second squared. All right. Whenever you do a problem at the very end, ask yourself, does the number make sense? And you go, what is an acceleration that I know, that I have a good intuition about? And the answer is obviously gravity. Gravity is, you know, the acceleration due to gravity is something that you experience every day. And so the acceleration due to gravity is 10 meters per second squared approximately. And so this is basically going to accelerate forward at 1/10 the acceleration due to gravity. Does that make sense? Yeah, it does. Okay. Like a car can easily, accelerate at 1 meter per second squared. What if I'd gotten 100 meters per second squared? Well, that would be 10G. And that's, cars don't do that. Okay. That would be like a rocket ship or something. So, you've got an idea that 1 meter per second squared kind of makes sense. Okay. And I set up the numbers, of course, for them to make sense. All right. So great. We've done the first law. We've done the second law. We saw that the first law really is a special case of the second law. The third law is very different, okay? So the first law and the second law really only correspond to one object at a time. The third law relates pairs of objects, okay, and the forces between pairs of objects. Forces don't just appear out of nowhere. If an object is experiencing a force, it's experiencing a force because some other object is exerting that force on it. All right? So for instance, right now, I feel gravity pulling me down. Well, what's causing that gravity? The Earth. The Earth is pulling on me. Okay? So there's really two objects when I'm being pulled down. There's really two objects. Or in my car example, there really were two objects there, although we focused on one of them. We focused on the car. There's still the Earth, and the Earth is pulling on the car. The third law relates the forces that of the Earth pulling on the car and the car pulling on the Earth. That seems counterintuitive, and that's because the Earth is so much bigger than the car. But the third law basically says that if object A exerts a force on object B, then object B exerts a force on object A, which is equal in magnitude but opposite in direction. Okay? And so you've always got at least pairs of objects. I mean, there could be more objects that are exerting forces on one another. These are called many-body problems, where many objects are exerting forces on one another. But just, if you want to simplify that to just two objects, you can't have one object like isolated without and have a force on it. Like, you won't just have one object with a force on it. There's always some other object causing that force. Okay, and so here we have two objects, A and B. If A is pulling on B with so much force, then B is simultaneously pulling back on A with the same strength of force, same magnitude, but in the opposite direction. Okay, and so that's how Newton's third law works. It always pairs the objects and pairs the forces between the objects. All right, so I tried to draw that here with a fairly abstract picture. And so here I have object A and I have object B, and you can see that object A here, object A has a force Fa on it. What is Fa? F is the force on object A, but because of B. So B is causing force Fa on A. What Newton's third law says is that simultaneously there has to be a force on B, FB, because of A, caused by A. So FA is being caused by B, FB is being caused by A. All right, because they're exerting forces on one another. And the third law says something else. The two forces are equal in magnitude and opposite in direction. As vectors, you can write it like that with a negative sign, because this basically says FA and FB, they have the same size, the same strength, and the negative sign just means opposite direction. Okay. Now, this is fairly abstract, but that's because I'm trying to apply it to every possible situation in which Newton's third law would act, and so the concept is necessarily abstract. But it could be simple as something as simple as like you have a box, and you're a person pulling on the box. As you pull on the box experiences you pulling on it, but you experience the box pulling back. Okay, and you can feel that, like in the tension of the rope. All right, or my next example, you've got two people pushing on one another. All right, let me actually bring it up here so you can see it. Okay, so we have here two people pushing on one another. Person number one is pushing on number two. Simultaneously, person number two is pushing on number one. I have them here on roller skates so that they can actually move apart. So, if you just do this and one person's pushing there and the other person's pushing back, they'll push, and each one will feel the other one push them back. Or in a tug of war, one team feels the rope being pulled one way, the other team feels the rope pulling them back in the opposite direction. These are all examples of Newton's third law. We'll do problems with like boxes on inclined planes with pulleys, and in those examples we'll have two boxes, and one box is exerting a force on the other one and vice versa. Okay, and so there will be applications of this, but right now let's try to get our heads around it. Okay, so the law is both intuitive and not. Okay, it's fairly intuitive when it comes to situations where both objects are roughly the same size. Okay, so for my first example here, I have two people and they're the same size. By size, I really mean mass. Okay, so here's person number one and M1. So that's a little subscript 1 on the M there. M1 has a mass of 100 kilograms. Person number two has a mass M2 of 100 kilograms. Okay. By the way, you'll see me using subscripts quite a bit in this next section, and what the subscripts mean is M1 would be like mass of person 1, M2 is mass of person 2. Okay, like that. All right. So the two people here have the same mass. They're both 100 kilograms. And then I go ahead and I say to you that person number 1 is pushing on person number 2 with 10 Newton force. So person 1 here pushes on person 2 with a 10 Newton force. And then I ask question A, how hard does person 2 push back on person 1? It's obvious that person 2 is going to push back on person 1. And the answer, Newton's third law, will say, well, it has to be 10 Newtons because the two have to be the same. 1 pushes on 2 with 10, 2 pushes on 1 with 10 Newtons. Okay, great. Now the next question is, what is the acceleration of person number 1 and what is the acceleration of person number 2? Okay, so I put them on roller skates. Again, my drawing skills are terrible, but these little circles here are supposed to be like roller skates. So you can see, when the two people push on one another, they're going to push one another apart from one another. And both person number 1 and person number 2 are going to recoil in the opposite direction from one another. Okay, and there are YouTube videos, by the way, where people demonstrate this. Okay, so I want to know how fast is person number 1 and person number 2 accelerating. Okay, and in what direction? Well, we actually don't have to do both person 1 and 2 because this is totally symmetrical. Okay, so you start off by drawing this free body diagram here. Okay, so you can see here I've got the person drawn there like that. Okay, and I've isolated person 1. That's what this free part of free body diagram means. It means just isolate one object at a time, so you don't confuse the diagram with too many objects, because there's a bunch of forces acting on one and there are a bunch of forces acting on two, and if you were to draw them all together, it could get confusing. So we're just going to look at object number 1. Here it is. So object number 1, the person has a mass of 100 kilograms, and so the person's going to have a weight of 1,000 newtons. Just multiply by G, 10. Okay, so 100 kilogram mass, 1,000 Newton force. Okay, just like the car, because they're on the surface of the earth, the ground is pushing back up, so there's 1,000 newtons normal force up, and those two are going to cancel. Okay, so there's no acceleration up or down, which makes sense. It's not like the person's going to lift off the ground or dig into the ground. They're going to move, horizontally, and so there's no vertical acceleration at all. There's no vertical net force. Okay, but there is a net force of 10 newtons back. Okay, and I call that F1 because it's the force on person number 1, but because of the actions of number 2. Okay, so F1, 10 newtons. All right, so when you add up all these forces, the up and down force cancel, just like they did with the car example, but there's a net leftover force of 10 newtons. Okay, and so you could see here, I say, all right, there is a 10 newton force to the left. All right, and always remember, both the magnitude, 10 newtons, and the direction, because they are vectors to the left. Okay, and then you say, well, I want the acceleration. Just do F net divided by m to get the acceleration. F net is 10 newtons. The mass is 100 kilograms. 10 divided by 100 is 0.1 meters per second squared, also to the left. Why? Because Newton's second law says that the acceleration is in the same direction as the net force. So both of them have to be to the left. All right. Now, I'm not going to do person number 2 because it's obvious. You do the exact same thing. You get the mirror image of the free body diagram here, like that. And you would just find that the acceleration would be 0.1 meters per second squared to the right. Okay, great. So now, that was pretty easy and fairly intuitive. Here's where the intuition gets a little messed up. Okay, it's when the two objects are not the same size. So here I have person number 1 has 100 kilogram mass, and person number 2 is like 50 kilograms. Okay, so person 2 is half the size of person 1, say a child and an adult here, like that. Okay, so person number 1 pushes on person number 2 with a 10 newton force. Same situation. So person number 1 is still pushing just as hard. Okay, and I want to ask the question: how hard does person number 2 push back on person number 1? Well, you might be tempted to say, well, the bigger person pushes with a harder force than the smaller person, but no, that's not the way it works. The third law doesn't say anything about the size of the objects. Whether object 1 and object 2 are big or small does not matter. Okay, if person 1 is pushing on person 2 with 10 newtons, then guess what? Person 2 pushes back with 10 newton force, okay, despite being smaller. All right, so at this point, it might strike you as counterintuitive. I'm going to try to fix that for you in a second, but just keep in mind, or just make sure you understand that the third law, the way it's stated right now, says that if 1 pushes on 2 with 10 newtons, then 2 pushes back on 1 with 10 newtons, despite the size. Okay, so what's going on with our intuition? All right, so part B of the problem, we're answering the same questions, is let's calculate the acceleration on each of the objects. Well, we don't have to do the acceleration on person 1. We already did that. It's the free body diagram would look the same, and we give the same result of 0.1 meter per second squared to the left. Let's do the free body diagram for person number 2. Okay, so here's person number 2, the smaller person. All right, now the smaller person has a 50 kilogram mass. That means a weight of 500 newtons. So you can see here I have Fg. That's the weight. That's going to equal m2g. Why did I put that little 2 there? Because this is the mass of number 2. Whenever you have more than one mass, so that you don't confuse the masses, put little subscripts on them, 1 and 2. Okay, so because otherwise you might go, oh, m is 100. No, not for person 2. For person 2, m2 is 50. 50 times 100, sorry, 50 times 10 is 500 newtons. Okay, so person number 2 has a weight of 500 newtons, and of course the normal force has to also be 500 newtons so that you don't get any acceleration up or down. Okay, F2, which is the force on person number 2 because of person number 1, is also 10 newtons. Okay, as above. All right, but now what's the acceleration on person number 2? Well, let's use Newton's second law. A is equal to F net over m. F net is 10 newtons divided by 50 kilograms. 10 divided by 50 is 0.2 meters per second squared to the right. So look at what just happened. Let me go back up to the diagram over here. The acceleration on person number 1 is 0.1 meter per second squared to the left. So the acceleration on person number 1 is 0.1 meters per second squared to the left. The acceleration on person number 2 is 0.2 meters per second squared to the right, twice as big. Even though the forces between the two are symmetrical, Okay. The acceleration is not, because number two has a smaller mass. And that's where your intuition is getting caught up. You think that person one pushes on person number two harder because person two accelerates more. But that's not the way to properly think about it. The way to think about it is the two forces are equal to one another. Person one pushes on two with 10 newtons, person two pushes on one with 10 newtons. But when you divide by the mass, the smaller object would have the bigger acceleration. Okay, and so it is consistent, and hopefully this is going to fix any kind of counter intuition that you might have to what's going on, and give you a correct understanding. It gets even worse. The bigger object one is than object two, the more asymmetrical it becomes. And so in the case of gravity due to the Earth, it gets really weird. If you're like person number one here, suppose you got a person, they're falling. So that if the person that's falling has 100 kilogram mass, that's 1,000 newtons force. That means that the Earth is pulling down on this person, say a skydiver, pulling down on this person with 1,000 newtons of force. You know what the third law says? The person is simultaneously pulling up on the Earth with 1,000 newtons of force. So yeah, Earth is pulling down with 1,000 newtons, but the person is pulling up on the Earth with 1,000 newtons. And you go, that's crazy, because I don't see the Earth move. Of course, 1,000 newtons divided by the mass of the Earth is an absolutely negligibly small amount of acceleration. Okay, and so that's why you just see the person pulling down, the Earth pulling down on the person. You don't see the person pulling up on the Earth, not because it's not happening, because the effect is so small that you can't see that acceleration because the mass of the Earth is so much bigger. Okay, and so your intuition gets worse and worse and worse the more asymmetrical the size of the objects are. The bigger M1 is compared to M2, the worse your intuition gets. But we're not going to be in that extreme situation. But when we do have boxes of different sizes, there when we draw the tension in the rope, you'll see these problems. If we say that mass 1 pulls on mass 2 with 10 newtons, then we have to say mass 2 pulls back on mass 1 with the same amount, irrespective of the fact that they're two different size boxes. Okay, so well, there you go. There's Newton's three laws, and the next lecture will be on just solving problems using this. The problem solving is not so much mathematical as it is procedural and conceptual. And so even though you're not going to use any fancy kind of mathematics like calculus or anything like that, and even the way I do it with the vectors, it becomes fairly straightforward. Still, students tend to get a little bit confused because it's mostly a conceptual procedure. And so what you really need to do is think about the steps and how you solve these problems, and in the back of your mind always keep these three laws. Okay, on a test I will ask you to know these three laws, but I won't ask you to write them because our tests are multiple choice. So what you're going to wind up doing on a test is just picking between the different choices. I'll say things like I don't know, I'll say something like there's no net force, therefore the object will accelerate. Well, no, if there's no net force, the object will not accelerate. So that's how you can decide which is a correct and which is an incorrect answer. So there are ways of making sure that you conceptually understand these problems, these laws. Okay. All right. Thank you very much, and that's the end of our lecture.